Hello, I'm Robert Smith, Director of the Weitzman School of Design's Master of Science in Design, Robotics and Autonomous Systems degree, or MSD-RAS. The post-professional RAS program explores the integration of robotics, material fabrication, and design computation in the pursuit of architectural design, manufacturing, and use. The degree considers how one goes beyond automation towards more intelligent means of engagement with the world, addressing the fourth industrial revolution's shift to bespoke, user-centered, on-demand autonomous systems. And right now, transformative changes in architecture and construction industries are afoot with the rise of the fourth industrial revolution. Rapid developments in robotics, artificial intelligence, and material science are giving rise to autonomous manufacturing capabilities. On the right, you see a 3D printing in metal that produced a rocket, but also produces this pedestrian bridge by MX3D. And here we see more low-tech Adobe structures 3D printed in clay by WASP. In this context, the way we currently design and build is far from perfect. Buildings carry severe environmental, social, and economic impact. And while these technological advancements offer a lot of possibilities, they also threaten to increase inequity, consumption, and waste. So we need new approaches that can reduce the environmental impact while meeting the increasing need for building and making those buildings more affordable. And we can do this while also increasing our creative design freedoms. And while design and construction typically considered very separate activities, there's an opportunity to consider how they could operate as an integrative creative act. To address this and explore these ideas, the MSD-RAS degree operates primarily through the production of robotically fabricated prototypes. Students actually undertake 3 design studios over the course of the degree, and these are undertaken within our state-of-the-art robotics facilities, where we have a wide range of tools and materials, and students gain a lot of hands-on knowledge operating these various robot platforms. All the work you do in the RAS program is in teamwork, as the real world tends to operate mainly in teams, and we believe it's the best way to do cutting-edge novel work. Programs also taught by a multidisciplinary faculty who specialize in many different areas, and each is a leader in their own field. And their expertise ranges from all kinds of things, from robotic fabrication, construction, to additive manufacturing, scientific research, theory and discourse, machine learning, mixed reality, human in the loop, you name it. There's a lot of expertise in these faculty that will be teaching you. In the RS program, design operates through parallel thinking across an integrated curricula consisting of design, technology, and theory courses. In fall, we do 2 design studios, each with different materials, manufacturing methods, and professors, and each is paired with a different technology course. In spring, all courses contribute to a common project that's realized, once again, as in all the other studios, in a fabricated prototype, but also in a thesis book. So the theory seminar is run by Emek Ödülü, and it covers topics such as cybernetics or politics making, and also incorporates some amazing guest lecturers, as you can see here. The 2 fall design studios work on a variety of different manufacturing methods and materials over time. This is a ceramics additive manufacturing studio that Andrew Saunders has just run. It just ran this fall, and as you can see, that this is one group that have produced an awful lot of work in 8 weeks and are presenting that work to a knowledgeable and friendly jury and learning a lot, not only from the jury, but through applied learning, basically producing this prototype and all this digital work within that period. To give you a bit of a sense of the breadth of that work and what students are doing in those 8 weeks, here's a bit of a clip of some of the activities they're undertaking. In this case, operating industrial robots for additive manufacturing clay. Learning all about ceramics and firing, bisque and glaze firing processes as well. exploring digital design workflows that included convolutional neural networks to develop these kind of micro features on the additive manufacturing process. And working with sensor feedback and cyber-physical systems to incorporate additional functionality within prototypes, in this case, such as sound. Another fall studio has explored designs that leverage robot hot wire cutting. This starts with the design of component parts. In this case, they were inspired by constructivist artists Pevsner and Garbeau, and utilize convolutional neural networks to inform studies and also to develop larger field organizations. In these projects, there's a strange interface between the digital, robotic, and the physical domains. Image content's translated back and forth to 3D ruled surface geometries and fabricated in EPS foam into partial mock-ups for ceiling designs that are then developed into larger ceiling scapes. This is another example that started with images from a convolutional neural network. Now you can see a 3D modeled ceiling and a part of a prototype that you just saw at the end. Each ceiling in this series aims to leverage robotics to produce an architectural order that explores heterogeneity and a variation in part-to-whole relationships. And the prototype students produced at the end of that design workshop were integrated with sensor-based adaptive lighting schemes. So this is one example here. And that's basically having the design studio and a technology course running in parallel and working on this project together. Another example of a fall course in fiber composites looked at filament winding. Here you can see designs that are partially determined through the development of jig and computer-coded weaving operations students are developing. And this enables the fabrication of very lightweight design prototypes, such as this bundled structure you see here. They're quite materially efficient, these designs, but they're also constrained a little bit by the fact they have to be cured in a kiln. This is pre-preg carbon fiber, so the resin has to be cured. This design that you're looking at here produces a lot of volume, but it's actually made out of flat pack parts to deal with that, those constraints. In parallel to that, Design Studio was a computational design seminar looking at how material placement would operate algorithmically in relation to design and manufacturing considerations. You can see an example of one of the group's computational design approach here. And how work like that is directed towards also site adaptation. That gives you an overview of some of the fall design studios. We typically run 2 8-week short intensive workshop design studios in fall. In spring, you work on a single project across 4 classes for the whole semester. These are the 4 classes. The design studio, material agencies, is coupled with a scientific research and writing, experimental tooling, and advanced RAS programming course. So students are not only working across the project in these 4 classes, but it's more of a research-led studio, starting with a kind of literature review and an understanding of what's state-of-the-art elsewhere. The studio typically takes a critical approach to production. Students develop their own thesis, but within some kind of specified framework. For instance, in the last few years, we've been looking at architectural ceramics and how we can move from fortis production towards more bespoke manufacturing while compressing multiple design performances and effects within matter. And we explore things like robot motion and how it's capable of producing material effects. So this is a computational approach to additive manufacturing in ceramics. And also looking at materiality and how those effects produce various visual character through different material glazes and things. So in the MSD-RAS, we don't adopt materiality, we engage with it, and prototypes inform design outcomes. This has also been questioned alongside the learning of advanced real-time robot programming and augmented reality and human-in-the-loop interactions, and the consideration of scaling and for industrialization, and also robot tooling. So in design research projects are worked on in groups and primarily based on students developing custom manufacturing processes and robot tools. For instance, trying to reduce waste, but also trying to create new creative possibilities. And this is an example of a project that developed a new incremental clay forming method that doesn't require formwork, and where the project tried to expand the agency of design to address issues not easily explored without that kind of technical knowledge that's developed. So in this project, a hollow core ceramic cladding was designed to transport urban steam waste to help grow community gardens in urban residual space. The generative design methodology connects areas of high solar exposure to steam vent locations. While the speculative design of that project is also supported by the development of this kind of full-scale mock-up prototype, as you see here, which is the emphasis really of these projects always. So this is a second forming project that basically adaptively manufactures to achieve a certain lighting level, and does that by using computer vision. It's actually a two-step process. There's a forming process that thins a porcelain ceramic to make it translucent, and then there's a perforation logic too. And these are driven by computational methods that students develop. And that finds its way into a facade screen that is both translucent and perforated, as you can see here. All the designs in the spring semester are always accompanied also by an architectural scale application scenario. Students aren't working on the planning of those, really just kind of the implications of design at a scale larger than their prototype. Recently, two projects have also critiqued industrial die cast extrusion's inability to vary production outcomes, and have looked at hybridizing the method with 3D printing to enable a more dynamic extrusion path. So this project is basically doing research and development on an end effector tool, extrusion dies, material and robot motion, and computational approaches to architectural design that leverage the method. This is an incredibly fast way of working. While 3D printing is very slow and incremental, die-cast extrusion is incredibly cheap and fast. On a robot, you're able to vary that trajectory. And those trajectories can also be generatively designed within facade schemes using algorithms that students write. This is an example of a kind of bundled facade screen and a prototype developed by students with a few different configurations. This is a second project kind of building on a similar theme, except with very different design and research inquiries into the manufacturing process itself, and also in its kind of application here, being more of a kind of relatively freestanding 3D almost bundled structure itself, forming stability through bundling of a kind of multi-layered facade screen. You can see how, I mean, that video is sped up, but not by much on the left. So it's an incredibly fast and efficient manufacturing process. And, you know, students, while they're developing those manufacturing processes, are also developing the computational methodology for designing facade screens, in this case, relative to that method. And fabricating a multi-part assembled prototype In this case, positioning the parts was really difficult. There are three-dimensional parts. So mixed reality application was used, in this case, hologram, to help support informing the team where each part needed to be in the assembly, which was much more effective than using construction drawings. That's the final prototype there. And a few other examples of spring-based projects include projects looking at slip casting. Slip casting is a really great ceramic method for producing really clean, complex final parts, but you need a mold, and basically you normally fill that mold with slip and then remove the slip after a period of time, and a cake would have formed on the inside of the mold that's a thin layer of the slip that becomes a ceramic part after it's fired. It's excellent and it's used in sanitary ware and all kinds of other applications, but it's not really used on facade screens because architecture normally requires more variability in parts, and you would need a different mold for each different part. And a few projects have explored how to bring variation into this through robotics. The first one looked at marbling, like how you can create different color effects by mixing two different slip. And this is a cross section through one part. You can see the slip mold on the left. And these kind of marbled effects are achieved through a custom robot tool and robot routine. So this is the tool the students developed, and you can see that it has a series of different slip reservoirs, and it can essentially fill different proportions of two different colored slips into the molds. And then here's the end tool. And then using some routine students developed on the robots, programming directly on the robots, they basically reappropriate a rotomolding forming technique normally used in plastics to coat the mold with very thin layers of slip. And this enables these kind of colored marble effects and no wastage of slip. While these are still soft, they're also exploring how to do assembly through squishing, where these parts are actually bonded together through the act of squishing while they're wet, and then design and simulation models to simulate how one could develop larger assemblies that are based on squished clusters that are then assembled together. This is a kind of an example prototype of several squished elements coming together, and you can see variation there in the marbling effects too, from basically using the same mold but computer control variation of colored slip. The second project has looked at this through a different lens, how to vary the geometry of parts without changing molds. So the mold geometry is fixed, but by rotating the mold to a different angle, we're able to get a different part. And by rotating the mold in a particular way, that part, it can also have curved edges, not just straight edges. If you held the mold at a specific angle the whole time you're casting, then you get a flat cut by partially filling the mold. But by rotating, you're able to get something more curved. Students also developing simulation models to be able to approximate the forming based on a set of rotations and also the cake thickness. This process has also been really challenging because you create a thin edge, and that's overcome by, you can see on the right, creating a thicker edge through a series of experiments, but also through microdosing of slip during the rotomolding process. And so what you see on the left is a student designed end effector tool that microdoses the slip in the rotomolding process. And with that, they're able to create very controlled variations, geometrically varied parts with a high degree of curvature and thickness on the edge from the same mold. And in exploring geometry, They've looked at many different kind of periodic geometries. Their final prototype expresses both that variation of geometry, but also variation from the robot fabrication of the casting process. So in this part, what you see, this multi-part assembly, it has 28 parts, 16 unique geometries, but they're developed from only 4 molds, demonstrating an economy there, a reduction in waste, but also an expansion in creativity through geometric variation that, while it might not be needed in current applications of slip cast for things like sanitary ware, enables one to consider its application for facade screens. And this is their speculative design of a facade screen employing thousands of parts, where that variation becomes even more important. In RAS, students are also developing many other strategies for reducing waste. This is a kind of a special tool for sand formwork, which is obviously reusable, and various methods for additive manufacturing in 3D, in this case over a sand mold and a slip cast part, and on the right, dealing with non-planar 3D printing. And, there are challenges involved in this and research to develop means of doing it well. This is an example of some post-tension compression parts manufactured with non-planar 3D printing, and a whole series of parts that went into this facade prototype you see here. This is an example of students looking at 2 manufacturing methods and integrating both within a robotic workflow. So what you have here is nested rotating cast part amongst a 3D printed part. And this is only possible through a lot of material experiments working with these different manufacturing methods, but also working on robot pick and place routines where robots are basically placing slip cast parts, embedding them within the additive manufacturing process. And this is an example of a facade screen that has these freely rotating component parts embedded within it. I think this is probably the last project I might show you, or at least it's close to the last. This is an example of a project that tried to address the facade screen as a multi-species facade screen and trying to reduce bird strikes, but also providing resting places for birds within a facade, while obviously perforating it to allow for natural daylight and ventilation and things. So in this project, there's both a manufacturing method that is 3 parts. It's a kind of planar additive manufacturing, and then a non-planar 6-axis manufacturing. There's also smushing or kind of smearing, and there's a kind of computational design methodology for setting up the overall facade. The smearing or smushing is basically taking place soon after additive manufacturing, while the clay is still wet and malleable, and provides an extra texture that is suitable both in providing kind of visual effects, but also spaces where you can't really see it very well on this slide. I should have had a more detailed slide for you, but on the far right, that you can see a pocket there that's kind of a bird resting place. But there's a lot of variability in that project that comes through this kind of hybrid manufacturing technique that's both additive and manipulative. In these projects, they've started from a kind of literature review, understanding what is out there and already been developed, and how in the course of the spring semester, students can make a difference and develop something that would contribute novel research. And as a result of that, a lot of these projects have been successfully accepted and presented and published in conferences and their proceedings. In fact, the two students from last year are presenting this week at Acadia, and there have been several projects before that have also found their way. And you will, if you're interested to see what some of this work is like, then certainly take a look for these. Most of these papers are available for free on the web, and you can take a look at them. But I think these papers give an indication that the work of the program is not just speculative and exciting and interesting for you to learn, but the work that you do in the program also is meaningful and of value to the broader community. So the program builds knowledge and skills in a number of areas, and these are some of the core subjects. You can see we look into the use of robot platforms and tools for fabrication. You develop various ways of programming robots and using computation and simulation modeling within design and fabrication workflows. And also you'll learn things to do with reinforcement learning, other generative design with machine learning, multi-agent systems, and various other computational approaches. And also looking at applied autonomy, how you use things like sensor feedback and computer vision to make adaptive fabrication tasks. RAS provides you with a unique set of skills that will also empower you to take on an exciting career with a wider range of possibilities. So this is very different from a professional degree program in the sense that all your subjects matter kind of equally rather than just a design studio, and they teach knowledge and skills that could be applied in many different career fields. And you can see some of the areas that our students go towards as graduates are listed here. They are either going into creative practice, architecture, fabrication or construction industries, or academia. Also in the program, we sometimes do visits to buildings or startups or other companies. This is some examples you see on this slide. And we also have guest lectures on various topics related to what we're working on that go into, fabrication, construction, computation, and engineering approaches and so forth. Outside of the work you do in the program, there's also opportunity to work in research labs or the robotics lab in extracurricular work. This is my research lab, the autonomous manufacturing lab. Several RAS students have worked in the lab or currently do. This gives you a bit of an indication of some of the work we do in swarm-based construction, aerial additive manufacturing, our bespoke tooling, adaptive robotic manufacturing, and computer vision, and many other things. This is a full-scale house prototype that we're working on at the moment, myself and another professor, Masoud Akbazadeh. Students from RAS and graduates from RAS are involved in this project that will be built full-scale on campus. It's a novel precast concrete. You can see some tests on the left. You can see it's super thin, and it's using EPS foam robot hot wire cut formwork. This is what the house looks like on the outside and the inside. The inside's fabric, and it's a concrete that's very thin, very light, and the house is designed for disassembly, relocation, and reuse. And it's a collaboration with CEMEX's global research headquarters in Switzerland. And another professor in RAS, Andrew Saunders, recently with Erding McHenry Architecture developed this feature wall, full-scale feature wall for a local community library. It got built last year, and this involved many RAS students and had a relationship to the studio, the full studio that Andrew was doing in RAS. And you can see some RAS students here basically both developing but also testing a full-scale mock-up of a part during the design and construction process. It was a really beautiful project and exciting to see realized, and a great example of the fact that in RAS you're learning skills and knowledge that you can really apply both in your assignments in the program, but also after the program in built work, and that at Penn, we actually engage in a number of those building projects in-house as well, and that you can be a part of those. If you're interested to know a little bit more about the program and what makes it distinct and special relative to other programs, this was a paper that I recently wrote about the RAS program in the ACSA teaching conference this year. And it's not online yet, but it should be online at some point very soon, I'm sure. Also, we're currently working on a book of the first 3 years of the program that will be out sometime in the next 12 months, and will include a number of things beyond the work itself, interviews with students and essays from some of the faculty, and it should be a really interesting book for you to check out. If you want more information on the degree itself and are considering to apply, then there are course descriptions online on the website. You can see the link at the bottom of the screen. There's also some FAQs for any kind of questions that we seem to come across regularly, and a place where you can click to apply. Note that applications have a deadline. It's on the website, and check that regularly. And also we regularly have open house dates mentioned on the website too. Other than that, you can also reach out to me by email, and I'd be happy to answer any questions you have. So once again, the Master of Science in Design, Robotics and Autonomous Systems degree is a post-professional 2-semester program in the Weitzman School of Design. I hope you found this session informative, and wish you the best in your application, and hope that you'll come and join us this coming year. Thank you.